Okay, so today we're going to be looking at the reactions of the alpha carbon of carbonyl compounds. This is a continuation of what we've already been studying of our carbonyl compounds. We've already looked at our carboxylic acid derivatives and our aldehydes and ketones, and even conjugated systems. So this is just yet another thing that we can do with carbonated or carbonyl compounds. All right, now what we're seeing here is, along with the fact that a nucleophile can actually do a backside attack to a carbonyl and actually get that tetrahedral intermediate like we've seen, we also have the possibility that a strong enough base or nucleophile can actually deprotonate the hydrogens in the alpha position, creating a negatively charged species. Now, this is normally not something we expect to see, because if we actually go back into our textbook and look at like pKa's of standard alkanes or sp3 hybridized carbons, we have pKa's around 60, which basically was telling us that we don't have to worry about those H's just ripping off very easily. Turns out these alpha positions are going to have much, much smaller pKa's. We're still not in the acidic range, but we're right there on the edge of it. So we're seeing that these are held on to a lot less. And the reason can be explained simply by looking at the resonance that's possible. If I rip off a hydrogen off of an alkane, I actually can't do anything at all with that extra pair of electrons. They stay isolated on that carbon, which is why there's that instability, which is why that basically stays back over here on the reactant side. When we have a carbonyl alpha to it, and rip that H off, we actually can have this resonance come up here and move that negative onto the oxygen. So that resonance contributor stabilizes that species enough that we do see that these H's come off. Now, if we actually play around with what else is on there, we actually can make it easier. Like it turns out, as an ester, we get one more resonance structure. All right, so here's where we ripped it off. We can actually move that negative up, just like we saw on our carbonyl example, but we can also move this around and actually put a positive bit on there. So these extra resonance structure just helps us stabilize that much more, or the electron withdrawing nature of the oxygen helps stabilize it a lot more. Nitrogen does the same thing. Matter of fact, nitrogen can actually have a much bigger effect or worse effect based on what it's near. So nitrates, being very withdrawing, actually help stabilize that to come off, and we actually have an acidic a hydrogen there. That is actually in the weak acid range. Anything under 15 is going to be kind of a weak acid. And we're going to see that this doesn't necessarily need to be carbonyl, because I know last chapter we saw that nitriles are carbonyl-like, and we see they do the same thing here. They allow that H to leave easy enough that it's actually got a decent pKa there. And the nice thing that we can introduce now that makes it even more acidic is to actually look at our beta diketose. Now, beta diketose really just means that if you have a carbonyl, alpha beta from that is a second carbonyl. So these are very specific to carbonyls on either side of something that's alpha to both. So this is kind of like alpha to this carbonyl and alpha to this one, makes it very acidic. pKa's in that 10 range. And that really is because we have multiple ways we can distribute that. So those extra resonance structures help stabilize that ion. And various different common ones so we can see how they actually do behave. And you notice anything here in on, these are actually acidic. So if you put those in solution with water and they dissolved enough, you would actually see a pH effect. And these aren't all carbonyl compounds. Got nitriles here that are carbonyl-like, but down here, this 8.6 and even 3.6, it's actually nitro groups. Now there is an N double bond O there, so it is kind of near a pi system, but it's definitely not a carbonyl. But you will see that that H is going to behave like these alpha positions that we're going to see on these reactions as we go through this chapter. All right. First thing we're going to look at is something that happens kind of naturally to a small extent. and that is keto to enol tautomerization. Now, if you remember, Taltomers were something that were the only thing that's really different is we're going to move an H from one part of the atom molecule to another. And what's happening here is one of these H's is going to end up moved up here to the O, and we go from a keto to an enol, enol. Now, for the most part, it's safe to say if you have this little tautomerization going on, it's going to favor the keto side. The keto is much more stable than an ene with an OH right near it. Now, there are some exceptions or things that shift it towards the enol part. First one is those beta diketose. When they are actually formed, when we actually were to protonate this thing, we can see that that stabilization can help because we get this nice little six-membered ring-like structure, or we could just say the hydrogen bonds helping stay in place. And this one, we'd create a conjugated system. So because this thing has a couple things making it a little bit more stable, we see it a little bit more. It's no longer just 99 to 1, it's 85 to 15. It still favors the keto, but we're starting to see a little bit more stability. And one big exception is actually phenol, which is actually this guy right here. It's benzene with an OH. And if we actually viewed that as an enol, which it is, we might expect that phenol could go back here to this benzene with a carbonyl on it. All right, but this particular case, we lose the aromatic properties. It's no longer aromatic, which is why this one favors the enol version. All right. Now, mechanism for actually converting that enol through, or a keto to an enol form can be viewed under basic conditions. So we're seeing a base catalyzed reaction where the OH, or base, comes in there and deprotonates that alpha position, creating the ion. Now, we're going to specifically call this an enolate ion. Enolate ion is very specific. It's a carbanion that resonates with a carbonyl to move the oxygen, the negative charge up to the oxygen. Well, in this particular form, we could see how that extra lone pair on the oxygen could attack a water molecule. And it would just actually reprotonate the water and kick off an OH. And there, we've actually completed the cycle. The OH that came in comes out, giving us that base catalyzed transition. Well, along with a base catalyzed mechanism, there's also an acid-catalyzed mechanism. Very similar, except where the attack happens. The O, with those lone pairs, does the attack on the acid, kicking off a water molecule. That same water molecule, or one just like it, could come along and deprotonate that alpha position, allowing that electrons to move in there and recreating the double bond and getting rid of that positive that was on the OH, giving us our enol. All right, so technically that transition can happen under acid or base conditions. Now, if I want to actually do something other than just remove the H, if I want to actually replace it with something, I can actually do that with a little bit of acid as a catalyst. Now, we just saw how the acid can actually help create that enol, and that's kind of how this is going to happen. Instead of actually creating the enol, it's going to create a space for that chlorine to go in. Now, this is different. Before, if I tried to do just chlorine just like this, I needed a double bond, or I needed light, and then I could put it on an alkane. But this was just a CH2. This is not something that we would have actually been easily able to put a chlorine on, not specifically that location. If we did it with light, we could put it on any one of these places, but we wouldn't have any control over it. But chlorine and acid, this will definitely go on that alpha position, or this side. We have two different choices that are alpha. On this one, I don't really have two, because this side has hydrogens in the alpha position, but there's no hydrogens on that alpha position. But we're showing this because it'll go with chlorine or iodine or even bromine. Just put them in there with some acid and you can put one right in that alpha position. The mechanism shows us how this goes. So kind of like the acid-catalyzed enol creation, we're going to let the ketone or aldehyde, the keto, attack the hydrogen of an acid and protonate itself. Then we can actually remove that H and create our enol or enolate ion. Now, instead of actually doing anything like we did before, where we just actually have the enol conformer or tautomer, we're going to let the bromine get attacked by that double bond. So it attacks on there, the Br minus gets kicked off, and then we'll just come in here and deprotonate that OH that put on top and get to our single substituted in that alpha position with bromine. All right, if we try to do this with base, we end up actually replacing all of the alpha positions. And the reason that happens is, let's look at this mechanism here. We can try to explain why it happens and why it happens. So the OH does come in here and just deprotonates this and creates that enolate ion. Now that resonance structure, we're showing how the bromine gets attacked by that double bond, just like it did with the acid one, and we end up putting that bromine on there. All right, now makes sense that this could repeat because we did actually just use the base, and as long as we had some more base in there, we could just rip off another H, which is what actually kind of happens on this. The reason it's expected to go to completion, you could say, is because this particular species, if I were to rip that H off and look at the charge on that, that negative species is going to be slightly more stabilized because this bromine is withdrawing. So compare this particular enolate ion with Rc minus dot dot, but now a Br, and then our carbonyl, and then the R. Turns out that bromine stabilizes it. So as soon as this guy got formed, an OH very easily removed that H and kept it reacting. We don't really have any ability to stop that. So whenever we do this type of reaction with Br under basic conditions, we just use our halogen in excess. All right, now where we can take advantage of this is we actually can use it as an identification technique. So what we're going to do, let me actually specifically talk about this, how this haliform reaction works. What it does is it's going to help us identify methyl ketones. Doesn't matter what this side is. But reason this is so darn important, this one having 3 H's on there, we could do these two steps multiple times, and essentially, and I'm going to do it like this, arrow, 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 to say we're doing that 3 times, we would end up with Br, 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 and replace all of those alpha positions on this side with bromines. And it's just because once you replace one, it becomes more reactive. So replacing 3 is going to be a piece of cake. All right, now instead of actually worrying about what's going to happen to this side, because technically if we stop and think, if this instead of an R happened to be just a CH2, we would expect those 2 hydrogens now to get replaced if we were to actually put some more OH in there. You'd kind of expect that to come in and rip off one of these hydrogens. Kind of like this first step here, where this OH came in and rip off that hydrogen. However, what we find is this guy is now super darn attracted to the backside of this because all these electron withdrawing groups have made this really electrophilic. All right, when that happens, we end up with a tertiary resonance or a tertiary intermediate, just like we saw with our aldehydes and carboxylic acid derivatives. But this one's kind of neat because what's going to happen, is we're going to rip this off. This thing is now a decent leaving group, and we're going to end up with 2 things. CH2, and now this is back to a carbonyl, but with an OH, and this, I'm going to simplify this rather than write it out, is just a negative species. All right, now, even though that's not very super stable, it's stable enough that it does get kicked off, and it does this nice little one-way reaction where it basically comes in there, rips that H off. So we end up with two very unique products, O- and HCBr3. This would be bromoform. And just like chloroform, it kind of has a unique and somewhat sweet smell. So you actually could use this to identify if you're creating, if you have a methyl ketone. Now, iodoform or bromoform, while they have the smell, they're not going to be nearly as bad for you as chloroform is. All right, what's next? All right, next little neat thing we're going to do is we're going to replace a alpha position on a carboxylic acid. Now, I can't do a substitution of the alpha position with an OH, or I can't substitute the same way, because if I actually try to use acid to catalyze it, I just end up protonating up here, and we move our double bond back and forth, and no reaction happens. So I don't actually make this more reactive, and I don't create that enolate ion. If I try to do this under basic conditions, my OH just comes in here and removes that H because it's much more acidic. So under acidic or basic conditions, I actually can't do anything at all with that alpha position. So what we do instead is this HVZ reaction. And technically the PBr is one we've seen before, and that is just going to turn this into an acyl bromide or acyl bromide. And that's what we're going to see is happening very first. That PBr3 just turns that into a Br. All right. Now that it's no longer a carboxylic acid, suddenly this is going to actually react as an enol a lot easier, because we can technically now protonate it because this is no longer actually going to react the same way. It's actually a lot more attractive towards that. So our bromine goes on. We move that double bond around and we create something that looks much more like an enolate, and then we'll just have to kick off our proton by deprotonate it, and they're showing up with water here. I guess we should show an arrow coming up there and getting that. But it's a great way to put a bromine in that alpha position. All right, so how would we put an OH there? Excuse me. All right, so what we are going to do, if we wanted to do something like this, is we are going to do that reaction we just showed. So the HVZ, so it's PBr3 and Br2 followed up with a little bit of water. And this is going to put CH3, CH, COO, Br. And then I essentially need to replace that bromine with an OH, and I can just do a simple substitution with that. So OH minus. I actually don't have to worry about deprotonating this because I already have it deprotonated, so I can do an SN2 on that location and get our final product. All right, now if I wanted to do a substitution of an alpha bromine, and this should say of a ketone or aldehyde, I have a small problem. All right, so let's look at a ketone, and I'll just look at a very simple one, acetone. Actually, I need a slightly bigger. All right, so because acetone, if I actually try to do that, I'm just going to make bromoform. So I want to do something more, so I have more locations on here, and that stops it. All right, but if I actually tried to put and swapped out a bromine with something else, like what we did on that previous thing with OH, what we did see instead of doing an SN2, what it's going to do instead is come along here and pull off an H from this position. And the reason it's doing that is because if we pull that off, Allow those electrons to come down here, we can easily kick off a bromine, and we can end up with a conjugated system. So, substitution of the alpha bromine with a ketone or an aldehyde, you have to watch out for the possible formation of an alpha-beta bond, double bond, because they'll be conjugated. Because kicking off a bromine's piece of cake because it's a stable, good leaving group. So what we typically see is just a kind of a rule. We want to avoid that possibility, so we use much more weakly basic nucleophiles. As long as they're weak, we can go on there. Now, carboxylic acids can't do that same thing, so that's why we were able to use them before and just put that OH on there in excess. Can't do it with a ketone or aldehyde, though. All right, the next thing we're going to look at is purposely forming something called an enolate ion just for the sake of doing substitutions. Because this, if we put that excess OH in there and rip that off, we've made something that's very nucleophilic. And the resonance structures will stabilize it. And that's going to give us the advantage to actually treat it like a nucleophile. So what we also can do to actually make it a little bit easier is use this stuff called LDA. Now the reason this can be easier is because in this process we might actually, if we put the wrong nucleophile in there, create more and more OHs. So there's going to be times we need that alternative. OH is great. In the situations where we can't use OH, we're going to use this stuff called LDA, which is lithium diisopropyl amide. And it basically does the same thing. For a nice one-to-one relationship, you're going to get 100% of the enolate, and then DIA, which is diisopropylamine. Now, where this comes in handy is either way we go about creating that enolate ion, either with the LDA or OH. Once we've created the enolate ion, and it doesn't matter how we actually focus on it, it will behave like a nucleophile, and we can allow it to be a nucleophile in like an SN2 substitution reaction. Now this is standard SN2, so we want that to be primary or better, but almost any alkyl bromide or alkyl halide could be used as a reaction center. All right, now we do have to watch out under using OH, because unfortunately we have a similar thing that happens to like when we use OH to create the substitutions of like bromines. The OH can easily get regenerated, and turns out that this guy, and specifically that location, is a little bit more reactive than this. It's a little bit more reactive than this guy. So we're going to get mixtures. So if we actually want to do this under basic conditions, we're typically just going to use this in excess and let it replace every single location. Now what we can do to limit it, so if we only want to put a single R group on there, we can use LDA, because for every one LDA to our alpha position, we will make one enolate. So that one enolate, we actually just put enough of our alkyl halides in there to add just that one group on, and we can get a nice single substitution. Now we do have to watch out. This particular one, for instance, that is a stereocenter that's being created, and you will get a racemic mixture. Same thing kind of happens on this one. It is going to be racemic. All right, so let's try to apply that. Let's say we wanted to make this guy. Now, I can easily see two possible ways to make it. It's either taking 3-hexanone and letting this guy come in and get attacked right there. I should be drawing that arrow like that. Or I can have this one, and we're having this position attack right there. We just kind of reverse these two. And we kind of want to ask ourselves why one would be the better than the other. Well, it turns out this first one, biggest problem we have with this first one is I have two different positions and either one of them could be the enolate. And if I allow that to happen, there it is, I end up with two potentially different structures. And only one of them is the product we actually want. Yet, neither one of these are necessarily more stable than the other, so we would expect to probably get about a 50-50 mixture between these two. Yet, if we'd started the symmetrical ketone, the enolate that formed would be the same on either side, just on that alpha position or that alpha position, be the same location. So we only get the one product. So we actually, when we want to plan this, we want to make sure we have something like that going on to eliminate possibilities of mixtures. All right, those unsymmetric ketones actually can be problematic in the sense that if I start out with something that's non-symmetric, I am going to create two potentially different enolates and therefore two potentially different products. Fortunately, we can make some predictions. It turns out that the enolate here, this first one, having that negative out here all by itself, it is going to be stabilized back and forth, but this is easier to form because getting that big huge LDA into this side that just had two hydrogens is much easier. So we have something we're going to call the kinetic product. Yeah, over here, thermodynamic, we're making a more stable enolate because the double bond is between two things that are substituted. So this thermodynamic product is actually just a little bit more stabilized simply because of that. All right, because we have a kinetic and thermodynamic, we see that temperature actually plays in. We're going to get these on low temperatures and this one on high. And if we actually had these pictures lined up, oh, we do. So this is high and this one is the low temperature one. All right. Another way we can actually do the same type of thing and actually get that enolate to form is to actually make an enamine. All right, so the enolate was to actually make these two alpha positions more reactive. Well, the enamine was just a way of putting that, protecting that carbonyl. That's kind of what we did with it in the previous chapters. And it actually made an alternative that had that double bond there. Well, it turns out that makes this location nucleophilic. It's going to do the exact same type of thing. So we actually can do a substitution from an enamine. So we create the enamine with that trace of acid in our ring, and then we just allow that to a nucleophilic SN2 type of attack on an alkyl halide and put that new R group on there. And then if we just use their acid and water, we can remove that enamine and go back to a carbonyl. So we can actually put a single one on there without using the lithium salt. And this one actually does give us a lot of versatility, so there's a lot of things we can do, and it is very nucleophilic. So I can actually do a backside of attack to a carbonyl. I could do a conjugated attack on a I could do a conjugated attack on a conjugated carbonyl. Both of these actually end up giving us some pretty darn good results. Okay. Now, all right, I'm going to pause here. I'm going to do this video into two parts, and this is where we're going to pick up.